we will consider the case when the utility is increasing in rate. And this makes sense considering a lot of classical networking scenarios. Now, continuously differentiable will help us use Kkt conditions, concavity as well. You know, you can find a lot of actual scenarios where utility is increasing in the form, for example, of a logarithm, or even faster with the rate. So our utility maximization problem is the maximization over the choice of rates allocated to the flows or allocated to the routes. The sum of the utilities obtained by each of these users are. So here R comes out of the set of users. In other words, the set of sources. Let me repeat, if two different sources use the same route, we will still give them different, give them different indices. Okay, now we want to do this maximization subject to link capacity constraints. That are the sum of all the rates traversing a certain link L should be below the capacity of that link. So how do we find the sum capacity? I mean, how do we find the sum rates? We sum the rate of the flows that traverse that link. So overall users are, find those users that use that link L. When you sum their total, rates, this sum should be at or below the capacity of the link L. Moreover, of course, the rates are non-negative. So how do we solve this problem? First of all, let's see an example of this network utility maximization problem. Consider a network with L links numbered 1 through L and L plus 1 sources numbered 0 through L. All link capacities are assumed to be equal to 1. Source 0's routes includes all links, while source R uses only link R. So source 0 is this source that wants to send packets all the way from here to there. Okay. So this is source 0's route. All the other routes are 1 hop long. Okay. Consider logarithmic utility functions. So the utility of user R in its rate XR is log XR. Okay, then we want to maximize over the set of choices of XRs the sum of the utilities. And how many choices do we have for the rates of sources? Well, we have a total of L plus 1 sources numbered from 0 up to L. Right? So L plus 1. Okay. Subject to the following constraints. First of all, for every link, what is the total rate that goes on that link? The rate of the of flow 0 plus the rate of the flow that uses only that link. Okay, so for every link L, we have flow L, which brings a total rate of x sub L, and flow 0, which brings a rate of x0. This sum should be at or below the capacity of that link, which has been specified to be equal to 1 in the problem. So this is our inequality constraint. Also, we have the flow rates being non-negative, of course. So this is a constraint optimization problem with only inequality constraints. And then we have only one set of Lagrange multipliers, basically, associated with only the inequality constraints. Suppose P sub L is the Lagrange multiplier associated with the capacity constraint at link L. Let P denote the vector of Lagrange multipliers. Okay, then the Lagrangian is given by this function. Okay. Remember the Lagrangian, the definition of the Lagrangian a few minutes ago. Now, notice that Slater's conditions are satisfied. You can check that Slater's conditions are satisfied and that our objective function and our constraint function are differentiable. Therefore, we can apply the Kkt conditions. Okay, so set the derivative of the Lagrangian with respect to each x sub r to 0. That allows us to find the value of x0 in terms of the Lagrange multipliers PL, and the value of XL for each L in terms of, again, the Lagrange multipliers PL. Okay. Now, also remember the second condition in the Kkt conditions. Lagrange multiplier times this should be 0 whenever the Lagrange multiplier value is greater or equal to 0. Okay, by solving these equations together, we find that the Lagrange multipliers PL are given by L plus 1 over L. And substituting in here, we find that the rate of the long flow is 1 over L plus 1. And the rate of each of the short flows is L over L plus 1. So the short flows are essentially L times, short flows have L times the rate of the long distance flow. You may think that this is sort of fair because the shorter flows use fewer network resources. And in fact, there's a reason that this is fair, and we will see this reason soon. So this brings us to the end of this lecture. In the next lecture, we will continue with a discussion of fairness and with a discussion of various utility functions that achieve certain notions of fairness.